Yeah.
What we're reading right now is an assignment that you would submit like a document to.
Oh, is it?
Yeah,
Okay.
so there's things that make sense. He changed it.
Did he change it?
It's been changed.
Okay. Great. Yes.
How would you like us to submit the labs?
The labs, just upload your IPython notebook.
Okay.
Yep, just through Learning Suite.
So if we have an image with it, because you want us to display the image online, do you want us to like zip it together or?
Okay, so this is the thing, this is what I want you to learn about IPython notebooks. If you've done it properly, you actually don't have to zip anything. And whatever you see is what we'll see. That's what we want. If you host the images externally, probably it'll work. Like if they're on some publicly accessible server. But the burden's on you to make sure that we can see what you see. Does that make sense? So fiddle around with it, play with it, get comfortable. The reason I'm having you do this, by the way, is because you're going to be visualizing a ton of stuff in this class, and a lot of your notebooks will have visualizations in it. And there'll be things like plots of performance over time, and you'll just want to inline those. So I just want you to get comfortable figuring out like how to do that. Okay? Question, go.
So essentially, it's like a Google Doc. You paste the image in the doc.
So you have to be careful about pasting images into notebooks.
You just have to delete.
Yeah, you just have to make sure it all works. So whatever workflow works for you is fine.
You share it, you make like a public link, and then
That is one way to do it. Yes. Yeah.
So I would highly recommend, especially this first lab, like go into one of the TA office hours and have them open up the notebooks and see what they're seeing. Because I can see my image when I open up the notebook, they cannot.
Right, or go find some server that you know doesn't know who you are, right? And try to open it there, something like that. Okay? Okay, great. Oh, you know, I should be on this slide. Business. Okay, so homework number 1, so your first lab is due tonight. Any other questions about that? It's pretty straightforward.
So there was a thing that said like you can make sure to have appropriate like axes and
Yes.
plot stuff.
Yes.
Like under like how where would you use that?
Yeah, you don't. Okay, so in this particular lab, that doesn't matter, but in general, this is just a general expectation. So I decided to put it on the first lab, which is that your notebooks should be tidy. So when you do things like plots, you have a y-axis and an x-axis, and it's like performance over time. What we don't want to see is like axes we can't read and values that are all scrambled together. Okay? Tidy and legible. Okay, any other questions about lab 1? Go.
Where can we find the slide from like last time?
Dropbox.
Where can we?
So I've posted, so I emailed this link out via Learning Suite. I posted it on Piazza.
Okay.
So
I just added the class like yesterday, so I haven't gotten it.
okay, yeah. So if you just added, or if you haven't gotten the Piazza invite, go ahead and send me email,
Okay.
and then I'll help you out. Yeah.
Is there a reason we can't submit our notebooks just by sharing the collaboratory link with you and not having to actually like upload the notebook totally?
I haven't thought about that. Timestamps. Is that the reason?
He wants to figure out a way.
Let us think about that. I haven't thought through what it would mean. Okay, but that's a good suggestion. I mean, it would be easier. I can see why that would be easier. But yeah, the timestamp thing would be a concern. Yeah, last question, then we gotta move on.
Just on the timestamp thing, given that it is like linked through Google Drive, it does keep track of every edit and timestamp of it. So you'd be able to just say.
Yeah, but then you have to make sure that you don't edit it after you've turned it in, because otherwise it'll look like you've turned it in late, and we have to go check the timestamps and compare it, and
That's fair.
Okay, we'll think about it though. I see the efficiency there. Okay, any other questions? Great, then let's move on. I wanted to show you a little bit about what a DNN looks like, kind of in practice, just so you have a mental image of what's going on. So I found this beautiful visualization, and let me see. It's a little dark, so I'm going to put the lights here. Stand by. Aha. Ooh, that's nice. Okay, so this is just a little visualization of what a modern DNN looks like and the sort of information processing that happens as you go through it. So it's a little thing you run in your browser. And check this out. Ooh. Okay, so the idea is, so this is an image classifier. Okay, so the task is given an image, figure out, in this case, what number does the image represent. And so you can actually draw a little image here of your number, and it will show you what the DNN does as it attempts to classify this image. So for example, if I draw 5, this is what happens. So the original input is down here, and then it goes through several layers worth of processing. And the cool thing about this visualization is you can kind of zoom in a little bit, and you can mouse over any neuron, and it will show you the neuron. Can you see those lines kind of at the bottom? It'll show you which neurons a particular neuron depended on. So, for example, the neuron that my mouse is over right here is dependent upon this group of neurons down here. And so you can sort of see there's these different layers of neurons, and they're all that look like a slightly different version of that 5. And for those of you who know a little bit about machine vision, you'll notice that this looks kind of like oriented edge detectors. So for example, so the response of a neuron is white if it's positive, black if it's negative, and blue if it is 0. And so this particular layer, when does it respond strongly? When do these neurons respond strongly? Kind of on the diagonal edges. How about this group over here? When do they respond strongly? Vertical edges, yeah. And then you can kind of go over here. Sorry, that's a little tough to see. When do these ones respond? Over here. Horizontal edges, right? Okay, so the first layer is responding to edges, it's finding edges in your image. The second layer is a little more complicated. You can see the feature maps start to look a little more tangled up. This one, it's not obvious what it's responding to. And then these ones up here, so these ones, things start to get crazy because they start depending on multiple things below it. And then these ones similarly depend. And then there's these things up here, which are called fully connected layers. We'll talk about this later. And so this neuron right here is a combination of all those neurons below it. And then these ones are super dense combinations. And then eventually at the very top, it spits out 5. So it thinks that image is a 5. That's pretty good. So you can have some fun. You can start erasing bits of this and just troll the neural net a little. So now it thinks it's a 3. I'm not sure what I was. Now it thinks it's a 5. But actually, this is a probabilistic classifier. Let me see if I can do that. It actually predicts a distribution over what it thinks it is. So it thinks it's a 5, maybe a 7, and maybe a 3. And you can just have fun with this and kind of play around with it and draw all sorts of things. So let's draw another number really quick.
Draw a house.
A house. All right. Okay. Stand by. All right.
Totally an 8.
I mean, if you had to pick a number, maybe 8. Yeah. Okay, so the point is, I just wanted you to be able to sort of see this kind of in real time. It's kind of a fun visualization. Just so you have a little bit of a mental image of kind of where we're going. Information begins at the bottom, gets processed sequentially by these layers. Things at the bottom are seem interpretable, and then in the middle, it just goes crazy. You have no idea what's going on, and the answer pops out the top. Okay? All right. So with that, today, we're going to talk about me, we're going to talk about you, and we're going to talk about linear algebra, and we're going to talk about cats. And so let's go. So me and you. So first of all, I just thought you might like an introduction to who I am. So I'm Dr. Wiggett, like I said. I run something called the Perception, Control, and Cognition Lab. So my interest is in the combination of deep learning, decision making, and probabilistic modeling. I love thinking about agents. So think robots and how they perceive the world, that's the perception part, and how they think about the world, that's the cognition part, and then like what they do with their body, that's the control part. And I like to think about all those things together. And so our research draws upon deep learning and probabilistic computation and reinforcement learning and a bunch of stuff like that. Some projects that we have going on in the lab, we think a lot about autonomous agents and deep reinforcement learning. That's a thing that I just think is fascinating. Common sense reasoning, some drone stuff, some MRI stuff, and most recently some ASL, American Sign Language translation stuff using deep learning. And we're sort of always thinking about how can you build robots or other autonomous agents that integrate a variety of sensor data from the world, translate that into knowledge, and then act upon it. And so these are some of the questions that we think about. And then we build these cool like environments using Unreal Engine. These are sort of virtual playgrounds for our agent. and we try to do reinforcement learning in them, and we build agents like we use this little robot thing here, sort of. Okay, so who are you? I put together some statistics. I thought it was really interesting. So first of all, about half of you are seniors. The other half of you are graduates, either master's or PhD. So really interesting. It's almost a perfectly even split. I loved this side, but this is where you're all from. I wasn't sure what none meant. I was like, wow, maybe that's like some super ambitious freshman who hasn't declared a major yet. He's taking a graduate level class. So yeah, I don't know. Anyway, a lot of computer science, a lot of Acme, but then really a long tail of really interesting folks from around campus, all here. So it's fantastic to have everybody here. Okay, so let's dive into linear algebra. So what we're going to do really quickly is talk about some of the linear algebra that you should have known, but you've forgotten. And linear algebra is a prereq for this class. We're not going to spend a whole lot of time on it, but I want to spend this lecture and I want to help develop a very specific intuition in your brains about vectors, matrices, and how we combine them. Okay, so just a little bit of terminology roundup. So we'll often talk about vectors and matrices in this class. We'll try to anyway, lowercase letters for vectors, uppercase letters for matrices. The name of the vector, or the variable, that's that. So this is the type or the field of the vector. So this is a vector of real numbers. This is the dimension or size. So this is an n-dimensional vector of real numbers. And then this is what I call the math intimidation factor. So, so this is the math. So formally, what mathematicians are saying is saying X is a member, or it's a sub. It's an element of one of all possible vectors of length n composed of reals. So, but really what that means is this. It's a list of numbers, and there's n of them. You can even write it like this, and you'd be fine. Okay, so it's a list of floating point numbers. There's different fields you can define vectors over, so there's the complex field, there's the binary field, etc. If we ever write something like this, m by n, that means m rows and n columns. And you can just think of that literally as a two-dimensional array. Okay? Okay, so that's what we mean when we say vectors in this class. You can interpret vectors. Hopefully, you remember this as an oriented arrow with an origin, its tail end is here at the origin, and the pointer bit is wherever the numbers in the array land. So if this vector is composed of two numbers, A1 and A2, then you can think of it as a line from the origin out to there. Okay, you're good? And you can add vectors together, and you can subtract them, and things like that. So if we remember, we add two vectors, it's like we added A and B. They're both here at the origin. One way to think about that is if you take B and you put its tail at the head of A, add it over, and then you get the resulting vector A plus B. Okay? But really, practically, all you do is you sum up the components of the vector. Okay, you should all remember that. If you don't, please review the linear algebra stuff that I sent out. Here's where I want to start building some intuition that you may not have had before. There's this thing called dot product. Hopefully you've all seen it before. Who has not seen the dot product? Anyone? You ready? Okay, great, you've all seen it. Okay, so you know that the dot product is just the element-wise, take all the elements of two vectors, multiply them point-wise, and then you sum the whole thing up and you get a number. Okay, here's what I want you to interpret though. There's this very interesting fact about the dot product, which is if you take the vector A and you dot product it with u, then the resulting scalar number is the magnitude of A times cosine of theta, where theta is the angle between the vectors. Okay, so I want to talk about this. So I brought some vectors to help me out. They're cardstock reinforced this year. So they're going to last for years. It's going to be great. Okay, so these are both unit length vectors. What?
We're just going to say, you actually need the size of B.
Oh, yeah.
As well. Let's use unit.
That's right. You should. I'm so sorry. We're going to assume that u is a unit vector because that's u for unit. That's why you don't need that. Okay. You guys should never feel free to correct. You should always feel free to correct. Right. Okay, so here we have two unit vectors. Okay, so the dot product between these two vectors is, if these are unit vectors, then it's also meant great pointer. Then this is 1. This means the norm of the vector. That means this is 1. So it's just a cosine between them. Okay? So cosine, remember if the angle is 0, cosine starts off at 0. So what happens as these vectors, sorry, 1. Okay. When the angle is 0, cosine starts off at 1. Thank you so much. Keep me honest. Okay. So what happens as we move the vector like this? What happens to the cosine?
It gets smaller.
Decrease, 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 decrease until it gets to right
Boom.
0. Okay, and then
Always negative
until -1. Okay, so these two vectors are perfectly aligned. That's the only way you can get a cosine of 1, that the vectors are identical. But what happens when we get here? So they're orthogonal. Orthogonal means there's a 90-degree angle between them. Now the cosine is 0. How many ways can we have an orthogonal vector to say this one? So let's hold this one fixed. How many ways can we have an orthogonal vector?
Is this two-dimensional?
We have 3. This is clearly a 3-dimensional vector. Okay. It exists in 3 dimensions. There's an infinite number. Okay, so there's an entire subspace of vectors, which looks kind of like this. And all of these vectors are orthogonal to the first vector. Okay? So here's the point that I want to make with this. There's only one way to get a cosine of 1, but there's an infinite number of ways to get a cosine of 0. And a lot of machine learning, and deep learning in particular, is based around the intuition that the dot product between two vectors can be thought of as a similarity metric. So the cosine of the angle between it tells us how similar the vectors are. If they're pointing in the same direction, cosine says 1. They're very similar. If it's pointing in any of the infinite directions that are orthogonal, the cosine says 0. So dot products are an incredibly powerful tool in machine learning because we think of them as similarities. Okay? That's the intuition I want you to have throughout the course. Dot product equals similarities. Okay. So, little exercise. Yes, question?
So, is that saying that in some ways, or an orthogonal vector, right angle there is giving us a 0, which means they're not similar at all.
Right.
And pointing the other direction is going to be -1 then.
Right.
So, in some ways, are we saying that pointing the other direction is almost more similar than orthogonal?
Yes. Yeah, it's sort of like saying there's a million different, it's like being on the straight and narrow path. If you're on the straight and narrow path, you're going forward or backward, you're on the path. There's only one way to be on the path. But there's a billion ways to not be on the path. I'm sure that's like a analogy. It's not the first thing that came to mind. But yes, you're right. So actually, this one is very specific. And the reason that this makes sense is because if they're lined up, it basically means all the numbers in the two vectors are equal. And if they're not lined up, what does it mean?
They're also exactly opposite.
They have to be exactly the negative. So actually that's pretty, like there's a lot of structure between the numbers in the one vector and the numbers in the other vector. Like they're very connected, even if they're pointed in opposite directions. Okay? But yeah, there's only one way to be lined up and there's only one way to be pointed opposite. There's a billion ways, an infinite way, a number of ways to not be aligned. Okay. So dot product of similarity. Okay, I'd like you to get with your little groups, talk to your friends, talk to your neighbors. I want you to try this little exercise. So here's a little function. It's called distance between two vectors, A and B. And I've written out the Euclidean distance between the vectors. Hopefully you all remember this notation, but if you don't, remember this is sum. So sum, we're iterating over all elements of the vector. So we're summing over all of them, we're calling the index I. So this is like for I in length of A, do. And then we're going to take the ith element of A, subtract from the ith element of B, square the difference, sum it all up, and take the square root. Okay? So I want you to see if you can rewrite this using nothing but dot products. Okay? Is that clear? You can do this? Okay, so give me a group. Feel free to talk to people. Google it if you'd like. I just want you to play with this a little bit and see if you can figure it out. Okay? We're going to take 2 minutes.
What was your name?
I'm Piper.
Piper, nice to meet you. I'm McKeon.
McKeon?
Yep. So, do the square root of the sum